Hello everyone! This lesson opens a block of lessons about secret key cryptography. In this lesson, you will learn the model of two-party communication using secret key encryption, its pros and cons, and hear about the history of secret key cryptography. Symmetric ciphers, which use a single secret key, are a cornerstone in the cryptography palace. The underlying idea is straightforward. The sender and the recipient share a secret password to make their future communications unreadable to others. The algorithms have evolved through millennia, from encryption and decryption steps performed by hand to complex programs optimized for high-performance hardware. The presented scheme describes the traditional approach of secret key cryptography to secure communication. Alice and Bob have agreed on the cipher and the key to encrypt their future messages. Like here, it would be IS-256 with a 256-bit key. Alice uses the key to encrypt the plaintext and sends the ciphertext to Bob. Bob already has the same key and uses it to decrypt the message. A single key is being used by both parties, and encryption and decryption functions are essentially an inverse of each other, which is the reason why this type of cryptography is called symmetric cryptography. Symmetric ciphers are convenient for use in most applications for at least two solid reasons. They can encrypt arbitrary big data, and they're very efficient at it. They do, however, have a major drawback: the exchange of the key. Communicating parties need a secure channel to share the secret key for the first time, and any time they wish to change it or the key becomes compromised. A secure channel is one that the adversary cannot physically access, read, insert into, or delete from. For example, it's a personal meeting, a trusted courier, or a dedicated military communication link disconnected from the outside networks. For instance, for Enigma encrypted communication, the Army divisions used pre-printed sheets with keys for every day of the next months. And for one-time pad encryption between heads of the USA and USSR, a designated courier would deliver the keys personally. Both these scenarios are not feasible for most modern applications. Today, it is a common occurrence to have a private conversation at distance between people who have never met before. It is now unimaginable to expect every first contact to be delayed until a secret key is shared by secure physical means. The problem of exchanging the secret key was solved by another primitive called asymmetric cryptography, which will be covered later in this course. Symmetric ciphers have inherited the best from the past. They are largely based on combining the simple operations of classic substitution and transposition ciphers and applying them repeatedly. Thus, they are called iterated product ciphers. In 1949 paper Communication Theory of Secrecy Systems, Claude Shannon suggested ciphers built by combining simple operations such as substitutions like Caesar cipher and transpositions as a means of effectively improving security. In context of modern ciphers, transpositions are usually referred to as permutations. Symmetric ciphers were first used at scale in the banking sector, with the rise of the remote terminal-oriented systems in the early 70s. Mohammed Atallah invented the first hardware security module, which encrypted PIN and ATM messages and protected offline devices, commercially released in 1973. The Atallah box was a plastic card reader terminal and a customer identification system. The Atallah key block format was used for secure interchange of encrypted keys and pins between terminals and banks. The current cryptographic block formats within payment card industry and American National Standards Institute largely have the Atallah key block at the root. Around the same time, Horst Feistel and a team of research mathematicians at IBM Corporation developed a block cipher named Lucifer. It was meant for remote banking as well and implemented in IBM cash issuing terminal. Horst Feistel's paper Cryptography and Computer Privacy described the cipher and thus provided a template for the design of cryptographic algorithms. The paper also bears great historical importance for another reason too. Coming from a civilian organization, it challenged the government's undisputed central role as a master of area in cryptography. At that point, the NSA has acknowledged it was not possible anymore to forbid commercial use and development of cryptography, only to influence it. Subsequently, IBM Corporation developed a stronger version of Lucifer and submitted it to the National Bureau of Standards as a national standard candidate in 1974. With a few more improvements to the algorithm suggested by the NSA, it was finally published as a data encryption standard in 1977 and authorized for use on all unclassified data. The NSA's improvements to DAS, particularly reduced key size from 128 bits to just 56, have ignited public controversy about whether or not they made the cipher weaker on purpose or maybe introduced backdoors. Most importantly, however, they have ignited scalpless research and the academic development of cryptanalytic attacks that to this day serve as quality assurance techniques in the developments of new cipher. DAS is the standard against which every symmetric algorithm ever since has been compared. DAS remained the standard for another 2 decades until being deemed no longer future-proof and superseded by advanced encryption standard IAS in 2001, following another public competition. IAS provides excellent long-term security against brute force attacks and has since become the most widely used encryption method found everywhere from state secrets to personal Wi-Fi access protection. The underlying structure of DAS and similar ciphers is referred to as the Feistel cipher after its main creator. Another common design used in IAS is a substitution permutation network. The inner workings of these structures will be discussed in the next lessons.